Okay, in this problem we're asked to consider Diana, who has a utility function, sorry about that, utility function of u of xy equals xy squared. Good x costs $2 per unit, so here is px right here, and py is here, and here is our endowment. We have wx, or I should say omega x, omega y is equal to 3 comma 6. Okay, so that's our endowment, and we're asked to find essentially the optimal amounts of x and y that she will consume. Okay, so first we need to set up her budget, and so her budget is going to be $2 times 3. Okay, she's got a price of 2 on x, and she has 3 units of x. And we have $1 per unit of y, and she's endowed with 6 units. So the value of her endowment is 6 plus 6 or 12, and that's what her potential spendable income is. We sometimes call this the potential income. Okay? And she's constrained by prices as well, so we have to put her expenditures on the other side of the equation to x plus 1y. Okay? So that's her budget. Okay? And we can graph it pretty easily. So this is 6 plus 6 or 12. How many units of x could she buy if she devoted her entire income to it? That would be 6, and of course it would be 12 up here. Slope is minus 2. That's the opportunity cost of a unit of x. Next we want to label the endowment. That's 3 and 6. Happens to be right at the midpoint in this case, accidentally. Okay. And that's where she starts on her budget, but that's not where she'll end up consuming necessarily. In order to find out where she will consume, we actually have to maximize utility subject to this plain old linear budget constraint. So we have 12 equals 2x plus y. We can actually employ the Cobb-Douglas rule here. Okay, so our alpha is 1 and our beta is 2 in the utility function. So x star is going to be 1 over 1 plus 2, or 1/3, times m. Now there's no m in this problem per se, but we have an m-like creature here, which is 12. And we have the price of good x, 2. So you can confirm this the longhand way by setting slopes equal to one another and solving that simultaneously with the budget. But you will find, in fact, that 1/3 times 6, or 2, is her optimal choice of x. Her optimal choice of y is going to be then 2/3 times 12 over the price of y, which is 1, and that's going to be 8. Okay, so we would expect her to consume 2 units of x and 8 units of y. We would label that 2, 8, and we know this is a nice Cobb-Douglas utility function, so there's going to be a tangency. Again, my drawing's not perfect, but the tangency is going to be right there. Okay? Now, we can look at where she started the problem. She started at this point, the endowment, and she ended up at this point, which means that she ended up giving up some x. In essence, she was a seller of x, and she ended up adding y, which made her a buyer of y. Okay? So when we do endowment problems, we're often looking at how people end up in relation to where they started out. And we sometimes will be interested in whether they're net buyers or net sellers of the product. Okay? For practice, what can you do to this problem? You can change the utility function, solve it again. Change the prices, solve it again. Change the endowment, solve it again. Allow the endowment prices to change, and see how that changes our answer.